Now see here electrical resonance. We have already done resonance in 11th standard. So here what do you mean by the resonance actually? So resonance is a very common phenomena here among the system which can oscillate. You know, if the system has tendency to oscillate with the certain frequency, this frequency is known as the natural frequency of the system. Now in series resonance circuit, what happens here in this case? Here a circuit in which inductance L, capacitance C and resistance R are connected in series and the circuit admits maximum current corresponding to a given frequency of AC is called series resonance circuit here. So in this case of the LCR circuit here, when the current is maximum with the applied frequency, then we say that circuit is actually a resonance circuit. So let us discuss how can current be the maximum in the LCR circuit. Now see here in LCR circuit, Z is equal to under root of R square plus XL minus XC whole square. This is the resistance offered by the LCR circuit. Initially when the frequency suppose nu is very low, then Xc is very less, that is negligible, whereas XL is very less and Xc is very large. But if you keep on increasing nu, what happen? LC keeps on increasing and Xc keep on decreasing here. At the particular frequency, at a particular value of the frequency of the AC source, XL will be equal to Xc here. So at the particular frequency, XL is equal to Xc and this frequency is known as resonant frequency. See here, if XL is equal to Xc, then we can write Z is equal to under root of R square, that is R. This is the minimum impedance. So R is minimum here. So impedance of the LCR circuit is minimum when XL is equal to Xc. This is the condition for the resonance. Now we can write here when the current is, the resistance is minimum or impedance is minimum, obviously current will be here, peak value of current will be maximum, that is E naught upon Z, that is actually E naught upon R here. So in the resonance circuit, current is maximum here in the circuit. Now what is the frequency at which this resonance occurs? We can get XL is equal to Xc. So we can write omega R L is equal to 1 upon omega R C, where this is called resonant frequency, resonant angular frequency is omega R. So we can write omega R square is equal to 1 upon L C. So we can write omega R is equal to 1 upon under root of L C. So this is the resonant frequency, resonant angular frequency at which the current is maximum. We can write here 2 pi nu R is equal to 1 upon root L C. So it can be also written nu R is equal to 1 upon 2 pi under root of L C. So in this case, this is here the frequency is nu R, that is called resonant frequency. So now see here in resonant frequency, we can get the graphical relation for the current and frequency here, and graphical relation when we show here, we just take the different values of the resistances in the circuit. So we can draw the graph is something like that. There is I you have taken and here is omega, and the graph is something like this for resistance R1. This is called maximum value of current here. Similarly, if you are changing the resistance here, the graph you will be getting in this case, this is for R2 and this is for R1. Obviously, in this case here R2 is greater than R1 because the peak value of current for R2 is less. This is your I maximum. And this frequency at which this is happening, that is called omega R, that is a resonant angular frequency here. Now, also we can see here for the any two values of current here. For the two values of frequency, there is the same current. So omega 1 and omega 2, and here this we can take here the delta omega and delta omega. So we can write omega 1 is equal to omega R minus delta omega and omega 2 is equal to omega R plus delta omega. So we can write omega 2 minus omega 1 is equal to twice of delta omega. This is called bandwidth. So, now see here, these type of the resonance circuit are very important in case of the mechanism of the tuning the radio or a TV set. So, all the acceptor circuits use this resonance concept here, and this is about the bandwidth. Now, we have to see about the in detail about the quality factor. Quality factor means that is actually shows the sharpness of the resonance in the LCR circuit. Now, see a Q factor of resonance circuit or sharpness of resonance. So, see here sharpness of resonance is defined by using the Q value or the Q factor. So, Q factor or Q value is defined as the ratio of voltage across L or C and the voltage across R at the resonance. Now, see here, so we can write here Q value is equal to, here we can write VL upon VR, that is here I naught XL upon I naught R. So, you will be getting XL upon R, and now we can write here omega R L upon R. Now, here L upon R, omega R can be written 1 upon under root of LC. So, we can write 1 upon R under root of L square upon LC. So, that is the Q is equal to 1 upon R under root of L upon C. So, the Q value of the circuit depends on the R, L and C. If you are increasing the value of the resistance, Q value or the quality factor is actually decreasing here. For electrical circuit which we use actually, the value of the Q may vary from 0 to 100, but for electronic circuits these days, the Q is approximately or around 200 here. So, the quality factor is basically defining the sharpness of the resonance. Larger the value of the Q, it means more sharper is the resonance, more narrower is the resonance, and also we can say for the smaller bandwidth, sharpness of resonance is more here. So, this is about the Q value and Q factor of the resonance circuit.